if I'm flying along and I do a pushover with my helicopter, well, in the case of the airplane, you remember, it didn't make any difference whether I was doing a 2G pull-up or a 0G pushover. I still had the same amount of control and roll. I still had the same damping and roll. In the case of a helicopter, because that rotor is freely hinged at the top of that mast, all of the control is coming from the fact that there is thrust or lift on that main rotor that's producing the moment about the CG. And when I allow that lift or thrust to go to zero, the control moment that I have will go to zero, and the damping and roll will also go to zero. And if I'm flying along with my helicopter and I do a 0G pushover with the helicopter, I can tilt that rotor into the oncoming air. That will reduce the thrust to zero. At the same time, that tail may go up. Since I didn't touch my collective or my throttle, I still have the same torque on the main rotor, which means I still have the same tail rotor thrust. The thrust is now well above the CG of the helicopter and will be producing a very severe rolling moment to the right. So the helicopter will start to roll to the right. The pilot, sensing that right roll, may be induced to put in left cyclic to stop that right roll. But when he puts in left cyclic to stop that right roll, there won't be any thrust on the main rotor, and therefore there'll be no moment being produced on the fuselage to stop that right roll. It'll have no effect. Furthermore, because there is no thrust on the main rotor, there is no damping and roll, and there will be nothing to limit that rate of roll to the right. And the helicopter will start to roll very, very fast to the right. We can show analytically that you could approach a rate of roll to the right approaching 100 degrees per second within 1 second. Now, it still has the same gyroscopic lag because nothing has changed that. The rotor is still lagging behind and is tilting to the left. And that lag, the gyroscopic lag, is about 1/10 of a second. So if the helicopter is rolling to the right 100 degrees per second, that means that the gyroscopic lag is going to be about 10 degrees. Now, if the pilot also puts in another 9 degrees of left cyclic, you are now trying to tilt that rotor 19 degrees to the left as the helicopter is rolling to the right. Well, there's only about 12 degrees of clearance built into the rotor system of the helicopter to allow for that teetering or flapping. That would be typical for the R-22 or R-44. It's also about the same on Bell helicopters. Hillers are very similar, maybe a degree or so less, but they're all in that same order of magnitude, around 11 or 12 degrees of teetering clearance. When you're trying to tilt that rotor 19 degrees to the left, then of course it's way beyond what the clearance that's designed into the hub. It's going to contact its teeter stops. The teeter stops on the R-22 are the inboard face of the spindles contacting the side of the rotor shaft. And when this event occurs, the one spindle will contact the shaft on one side. Half a revolution later, the opposite spindle will contact the other side of the shaft, and the forces are tremendous. They are so great that they can either chop that rotor shaft in two or bend the rotor shaft, and in either case allow a rotor blade to come down and strike the left side of the helicopter. And of course you have a catastrophic type of accident when that occurs. And it's maybe just a little bit more complicated than the way I described. Because as that helicopter pitches forward and the tail rotor comes up above the CG, producing that rolling moment to the right, then there's also something else which can happen. The torque of the main rotor, the rotor is rotating in a counterclockwise direction. The torque reaction from that main rotor is in the opposite direction, or clockwise. If the pilot is too late coming aft with his cyclic to reload that rotor, then when he tilts that rotor back, he will be tilting that torque reaction from the main rotor, which is in this direction. He'll be tilting it back as well. And that in turn will put a rolling moment on the fuselage due to the torque reaction of the main rotor. And it's when that torque reaction combines with the thrust of the tail rotor that you get this very, very large, very, very fast roll to the right. And that's when the event can become really catastrophic. So it's very important when you have this feeling of weightlessness that you immediately give it a gentle half cyclic to reload that rotor. Don't wait until the helicopter has a very high pitching velocity nose down and then put in a large amount of half cyclic. Because if you're too late, then you'll get this combination which will cause the catastrophic right roll. So it's important to recognize the fact that you have a feeling of weightlessness and immediately apply just a gentle half cyclic to reload that rotor. Low G mass bumping constituted approximately 9% of all of our fatal accidents. How can it be avoided? One of the most important things is no abrupt full range control inputs. Caution new students. One thing we have found with the R22 is there are two different points at which we have a very unusual, very abnormal number of accidents, both fatal and non-fatal. And one of those 2 points occurs when a pilot takes up either a student or a potential student for a demonstration flight or for a sample or preliminary lesson flight, an initial flight. And it's on that very first flight where he's allowing the passenger or student to take the controls for the very first time. We have a very unusually high accident rate where that occurs. So before you ever allow anyone in that helicopter to take those controls, be sure that you really indoctrinate him very, very carefully, because that's one of the areas where you are most apt to have a fatal accident. Low G mass bumping, light in the seat, half cyclic. If you're performing any maneuver where you feel the least bit light on the seat, any feeling of weightlessness, immediately apply a gentle half cyclic and reload that rotor. Never dive, lower collective. Now, an airplane pilot is very used to pushing forward on his stick and diving an airplane if he wants to suddenly reduce his altitude for collision avoidance, to avoid birds, to avoid another aircraft. And that is a very natural reaction to the airplane pilot, is to go forward with his stick and literally dive the airplane. In a helicopter, that isn't the way to avoid an obstacle or a possible collision. In the helicopter, if you want to suddenly go down, you do it with the collective, keeping the helicopter nearly level as far as its attitude is concerned. The cases that we have had of low G mass bumping, to the best of my recollection, all occurred involving a high-time airplane pilot, very low-time helicopter pilot. And it's those airplane reactions in the helicopter that can be so dangerous and are quite often have to lead to a low G mass bumping situation. Never pull up and push over. One of the ways that you can get into that weightless condition, the easiest, is if you're doing a pull-up with the helicopter and then go to level off with a pushover, you can get into that low G or weightless situation very, very quickly, very easily. So if you do a pull-up for one reason or another, be sure that you level off very, very gently with the cyclic, and we're using some collective.